Start. So this is the fifth lecture of this Advanced Nuclear Physics 2. And okay, so today I will discuss some time-dependent extension of the microscopic mean field approaches. So to describe nuclear dynamics like fission or reactions or any excitations. And I will introduce this time-dependent Hartree-Fock theory, so which is a time-dependent extension of the Hartree-Fock theory, and also TDDFT, time-dependent density functional theory. Yeah, and yeah, similar to the static case, Hartree-Fock and DFT, this TDHF and TDDFT are closely related, especially in nuclear physics case. Yeah, and I will introduce similarity and difference and basic concept of TDDFT. And later, I will show some examples of applications to describe the nuclear reactions. Okay. So this is a reminder of the syllabus. Okay. So far I introduced Hartree-Fock and DFT, the mean field approaches, and introduced some pairing correlations. And in the last lecture, I discussed some methods to describe the collective excitations, the TDA, Tam-Dankov approximation, and RPA, random phase approximation. Yeah, and today I will discuss this nuclear dynamics. And yeah, from this lecture, the discussions will be more like applications. Okay. And yeah, in the next week, we will skip the lecture and then we will continue the discussion and applications for, especially for the neutron star physics. Okay. And so the purpose of today's lectures is the following. So yeah, as I mentioned, I will introduce the time-dependent Hartree-Fock, TDHF theory, and the time-dependent DFT, TDDFT. And yeah, before showing some applications, I will derive actually the random phase approximation, RPA, as a small amplitude limit of the TDHF. So we can derive actually RPA from TDHF. Yeah, and then I will show some selected examples of application TDDFT or TDHF or nuclear reactions. Okay, and demonstrate its usefulness. Yeah, and yeah, the main point is using TDHF or TDDFT, we can describe some complex nuclear dynamics, which is actually the many-body problem of nucleons from nucleonic degrees of freedom through the mean field description. Okay, so this is the main point. Okay, so let me first introduce the time-dependent Hartree-Fock TDHF theory. And again, so those guys, Hartree and Fock. And actually, the TDHF was first proposed by Dirac in 1930. Yeah, so this is a reference. Yeah, so we use TDHF approach to describe we can describe many-body fermionic systems, not only nuclear physics, but also condensed matter physics. But today I will show application for the nuclear systems. Okay. And here I just recall what was the Hartree-Fock theory. So this slide was taken from the lecture 2. And okay, so from the variational principle, we could derive the many-body Schrödinger equation if we do not impose any restrictions. So from the unrestricted variation of the energy expectation value, one can derive the many-body Schrödinger equation. And the point of the Hartree-Fock theory was to approximate the many-body wave function or trial wave function for the variation by a single theta determinant. So that was the point. So by introducing the theta determinant, we could derive the Hartree-Fock theory. Okay, and those were representations of the theta determinants. Okay, that we used in the lecture 2. Okay, and I will again use a bit of these formulas. So this is just a theta determinant composed of single particle wave functions, small phi. And this is just a compact form of this determinant. Okay, this is the second line. And the last line is showing the permutation, the summation over the permutation, any possible permutations. And this SGN provides you the proper minus sign according to the number of permutations. Okay, so this is just a definition. Okay. Yeah, and actually the TDHF theory is, can be derived again the variation principle. And so this is the action, S is the action, and the action is written in this form. So this is time integration of this HIH bar time derivative minus Hamiltonian H. Yeah. And if we do not impose any restrictions and by performing the variation for the Bragg state, you can easily get the time-dependent many-body Schrödinger equation. And okay, so this is just before going to the Hartree-Fock TDHF, I just show the property of the many-body, TDSE time-dependent Schrödinger equation. So one can derive this norm conservation by taking the time derivative of this norm of many-body wave function. So this differentiation operates on the Bragg and Ketz state. And by using this time-dependent Schrödinger equation, let's say TDSE, you can replace this psi dot by h psi divided by IH bar. And you can easily show that the first and second term cancels if H is Hermitian. Okay, so the norm is conserved in this way. And also energy conservation can be shown readily. So by taking the time derivative of energy expectation value and assuming that the many-body wave function is normalized, then the time derivative operates around Ketz state. And by putting this time in the opposite way, H psi can be replaced with IH bar del T psi. And you can get this energy conservation. So this is a basic property of TDSE, time-dependent Schrödinger equation. And now we will derive the TDHF theory. But actually, the Hamiltonian term is the same as static case. So we can skip the derivation for this Hamiltonian. And the additional term is only this time derivative term. Okay. And actually, this time derivative term can be calculated in the same way, almost exactly the same way as the one-body term. Okay, so here so remember that, okay. Okay. Remember that, so you can put the definition of theta determinant, and then you will get n factorial, 1 over n factorial times this the product and phi 1, phi n, and determinant. So let's say you have this determinant in the Ketz state. Okay, and the point was this. So you have the n factorial term coming from this summation. But okay, you can always replace the integration variables, and then you can make the Bra state in this order. Phi 1 R1, Phi 2 R2, and Phi n Rn, something like that. But by change, if we change the integration variable, then it corresponds to the change of the rows or columns. So we will obtain, it generates the minus sign, but which is proportional to the number of permutations. Okay. So the point was the n factorial term coming from this summation all provides the equal contribution. So actually, this summation and this 1 over n factorial cancels, and this, you will get this first line. So this was the first trick we used for taking the expectation value in the Hartree-Fock theory. So we just used this operation so that this line shows that, so we cancel this 1 over n factorial already, and the Bra state is just a product phi 1 R1, phi 2 Rn, up to phi n Rn. And in between this blanket state, you have this IH bar time derivative, and this remaining is a Slater determinant without this factor. Okay. And then, so this is somewhat different from the one-body operator, but the actual operation is the same. So in case of one-body operator, that was something like, so we can write in this way. And this Ti was just this kinetic energy operator acting on the ice coordinate. Okay, but now we can skip this. Okay, so the point was, okay. So this operator operates only on the ice coordinate. For instance, if I equal 1, this operates only on this phi R1. Okay. Then you will have this summation. And now, if you look at carefully, so this time derivative operator will operate in for the product of this function. First, this phi xi1 plus term operating on the phi xi2 plus blah blah blah. So you will again get the summation over these wave functions. So the operator looks different, but what we will do is the same as the one-body operator. So you will have this summation over I, okay, here. And this is nothing but this operation onto the ith single particle wave function phi. Okay. And since the single particle wave function phi is also normalized, this phi 1 xi 1 becomes a Kronecker delta, and any other terms except this phi xi I becomes Kronecker delta. Okay. And then what you will get is, so xi1 to xi(n) equals to 1, 2, 3, blah, 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 up to n. So this ascending order. And the final result is the same as the one-body operator's case. So this is a kind of expectation value with respect to phi star and phi. In between, we have IH bar time derivative and summation over I. Okay. So this calculation is the same as one-body operator. So then you can easily get the TDHF equation. So the right-hand side is the same as Hartree-Fock, the static case. And the left-hand side, if you perform the variation with respect to the phi star, you will easily get this left-hand side. So this is a time-dependent Hartree-Fock equation. Yeah. And it satisfies, again, the norm conservation and energy conservation. And in the same way as TDSE, time-dependent Schrödinger equation, you can show that the norm or this overlap between two single particle wave functions is conserved. Okay. And this is very important property. So by performing, static Hartree-Fock calculation, we can prepare static initial wave function of the atomic nucleus. Then we can evolve in time. And this indicates that the Pauli exclusion principle is automatically satisfied for all times during the time evolution. So if initial state is also normalized, then if we evolve in time, according to this TDHF equation, this orthogonal property will be automatically conserved up to the numerical precision, of course. Yeah. So this is one good property. And you can also show that the energy is conserved in the same way as TDSE. So again, this is a good property. So yeah, the total energy is conserved during the time evolution, and the Pauli exclusion principle is also conserved. So by just solving this TDHF equation self-consistently, the complicated nuclear dynamics can be described, ensuring this fermionic character easily. Okay, so this is what is TDHF, time-dependent Hartree-Fock theory. So this is just a extension by putting new term in the action, IH bar partial time derivative, and we can get the TDHF equation. Okay, now, so I will introduce this time-dependent density function theory, TDDFT. Okay, so in case of static case, Hartree-Fock and DFT are closely related. Okay, so this is just a slide taken from the lecture number 2. So in the static case, the concept of DFT was explained in this way. So what we'd like to solve is the many-body Schrödinger equation, but I explained that to solve this many-body Schrödinger equation is practically impossible because it is too complex. So what we'd like to do is to open this box to get the solution. But in practice, it is impossible. But in case of density function theory, DFT, what we solve is this Kohn-Sham equation. It looks very similar to the Hartree-Fock equation with local self-consistent mean field potential. And actually, according to the Hohenberg-Kohn theorem, one can show that the many-body wave function psi can be written as a functional of one-body density rho. So any observable which is given by the expectation value of any operator by psi can be written as a functional of density in principle. So this energy expectation value can be written also the functional of one-body density. So in principle. So if you believe this theorem, there exists some functional, energy density functional, which contains all the information of the many-body system, the right-hand side, into this function. Okay. And if this function exists, this constant potential can generate, some special potential, which as a solution of this quantum equation, one can get the ground state energy and one body density of this many body Schrödinger equation, the exact solution. Okay. So this energy density function, EDF, is the key to open this box. Yeah, so this was the situation of the density function theory. And I explained what is the Hohenberg-Kohn theorem, which was actually quite easy proof. And yeah, we could show that the one-to-one correspondence between the external potential and one-body density. Yeah, and it shows us the one-to-one correspondence of psi and rho, and giving us the existence of energy density function, EDF, which contains all the information of the right-hand side. Okay. So in case of static usual density function theory, Hohenberg-Kohn theorem and Kohn-Sham scheme were the principle, the basic theorem. And okay, so now I will introduce TDDFT. So we will use a bit different technique to show one-to-one correspondence. But first, I will explain the image. What is the TDDFT, the concept of TDDFT. But the situation is very similar. So what we like to solve is a n-body or many-body system. Okay, so this is a time-dependent Schrödinger equation for many-body system. Okay, but it is impossible to solve in practice. So what we solve actually is a time-dependent Kohn-Sham equation, TDKS. Okay, so it is again very similar to TDHF. Okay, or this is just a time-dependent extension of the Kohn-Sham equation. Okay, so the complexity is quite different. So for this, we just have n single particle orbitals, and we just solve this one body like Schrödinger-like equation, and the density, the potential is constructed from all the nucleons in the system. Okay. So those are looking different. But in case of density function theory, TDDFT, those are actually related to each other. So starting from some initial state at T0, according to the Hohenberg-Kohn theorem or static principle of density function theory, the Schrödinger equation and the Kohn-Sham equation can be connected. The solution of Kohn-Sham equation can be the same as the solution of the many-body Schrödinger equation if the exact energy density function, if we have exact energy density function. Okay, in principle, we can get this connection according to DFT. And then we evolve in time, and those systems evolve a bit differently. So they are obeying different equations, so they can be different. But the point is the time evolution, from the time evolution, we can show that actually the many-body wave function and the one-body density at time t there's a one-to-one correspondence. So in this case, the one-body density obtained from the time-dependent Kohn-Sham equation can be equal to the one-body density of this many-body Schrödinger equation, coming from the many-body Schrödinger equation. Okay. So I will show the principle how we can show this correspondence. So, but the point is, we will solve this TDHF, local TDHF-like equation, the time-dependent Kohn-Sham equation. But in principle, it can be related to the time evolution of the many-body Schrödinger equation. the system of interest. Okay. So here I just introduce in one page what is the basic theorem of TDDFT, which is proposed by this Runge and Gross, so Runge-Gross theorem in 1984. Okay. So we will just use those notations. Okay. So this is one body density law. This is just a definition. And this psi, I just abbreviate the coordinate dependence in psi. So, but this is just a definition of one body density. And here I introduce the definition of one body current density. So this is the current. And we can define in the usual way in quantum mechanics. So psi star number psi minus psi number psi star. Okay, so those are the definition of one body density and one body current density. And I will use this TDSE, time-dependent Schrödinger equations, for two cases. One is the system described by H and H prime. They are different only by the external potential B and V prime. So kinetic term and the interaction term are the same. Only the external potentials are different. So they are H and H prime. And the corresponding many-body wave functions are written as psi and psi prime. So this is just notations that we will use to show what is the Runge-Gross theorem. So in the Runge-Gross theorem, we start with taking the time derivative of the current density, one body current density, for the two systems described by H and H prime. Okay. So the left-hand side is just a time derivative of the current, the J and J prime. And you can put the definition of one body current density here and take the time derivative. And time derivative will operate this psi star and psi and psi star. Okay. And you can use TDSE to rewrite a bit. So again, you can use a time derivative of psi dot, let's say, can be written as h psi divided by IH bar. Okay. And yeah, already here I just replaced psi dot by h psi divided by IH bar. Okay. So this is just a equation coming from the definition of one body current density, and taking the time derivative, you can get these equations. Okay. So let's say those equations A and B respectively. Okay. And if you, by taking the difference A minus B, you will get this equation. So the left-hand side is just a difference of this side, J and J prime. And on the right-hand side, okay, so since T and B, this one kinetic energy operator and the interaction operators are the same. So if you take the derivative, the term proportional to those terms cancels. Okay. The only difference coming from this V and V prime, the external potential. Okay. And by carefully looking the terms, and you can show that actually coming from this nabla H psi term, you have the derivative acting on V prime or V, that external potential, and also derivative acting on psi. And from this nabla operating V, you can get these terms in the right-hand side. Okay. So by taking the difference of these two, you can obtain this equation. And this is an important equation. So it indicates that if the external potentials V and V prime are different, okay, so right-hand side, if the right-hand side is non-zero, then time derivative of the current density, J and J prime, will be different. Okay. So it indicates already that the correspondence, I mean one-to-one correspondence between the external potential and the current density. Okay, so it means that, yeah, the external potential can be different by some time-dependent constant. If it is a time-dependent constant, then nabla, that this spatial derivative operates to this constant, then it vanishes. So if the external potentials V and V prime are different, more than a time-dependent constant, then the current densities must be different. Yeah, okay, so it is given here. So, and also, you can use actually the continuity equation. Okay, so by taking the divergence of both sides of this equation, you have divergence J, and you can always use this continuity equation. Then you can replace divergence J by time derivative of the number density. So again, the left-hand side becomes the time derivative, difference of the time derivative of the number density, one-body density. So again, you can use the same argument that if the external potentials are different by more than the time-dependent constant, then the one-body densities must be different. I mean, time derivative of one-body densities must be different at certain point. And then it indicates that we can use the Taylor expansion around the initial state. One can show that this Taylor expansion must be different at certain order. So time evolution becomes different if the external potentials are different. So this is the basic logic of Runge-Gross theorem. So it shows that the one-to-one correspondence between the Hamiltonian and one-body density and the one-body current density. And in principle, you can solve, in principle, the time-dependent Schrödinger equation and the Hamiltonian and psi are related to each other. So it provides us the correspondence between the density, one-body density and current density, and the many-body wave function psi. Okay. So this is the basic theorem behind the time-dependent density function theory. So this is a bit different from the Hohenberg theorem, but in this way we can show that the correspondence between the psi and the densities. So now I will show how we can apply the TDDFT in nuclear physics context. So here I just show some examples. So for instance, here I show the so-called iso-vector giant dipole resonance, or it is a photoabsorption cross-section by triaxially deformed the heavy nucleus, osmium 188. And purple dots corresponds to the experimental data. And through the time-dependent linear response calculation, one can get actually this photoabsorption cross-section, and it agrees with experimental data. And also one can start from the elongated solution of the Kohn-Sham equation and evolve it in time and calculate the fission dynamics in real space and real time. And we can also calculate the heavy ion reactions by colliding two nuclei. I will show some examples later. And actually, by extending TDDFT to include the superfluidity, we can also describe the quantized vortex, which is a topological excitation of some pairing field. And yeah, I will show some application of this kind of context in the lecture number 6 or 7. Okay. So anyway, using the TDDFT, we can describe a variety of nuclear dynamics within the unified framework. Okay. So now, before going to the application of TDDFT or TDHF for the nuclear reaction dynamics, I will quickly show that we can derive the RPA, random phase approximation, as a small amplitude limit of the TDHF theory. Okay. So this is the so-called linear response theory. So, okay, so here I just recall, yeah, what was given in the previous, assignment number 2. So, yeah, the assignment was to derive the Hartree-Fock condition. Okay, so from the variation principle in the second quantization form, you can show that the single particle Hamiltonian matrix H satisfies this condition. So particle whole or whole particle components of H must be 0 according to the variation principle. So particle and whole means that, okay, whole states means occupied states, and they are described by index I and J. And particle states indicates unoccupied states, which are denoted by indexes M and N. Those are just a convention. And according to this convention, the particle whole components and also whole particle components must be 0. This is a result of variation principle. And I will just use this relation in the following. So using this property, not this property, but using the property of one-body density matrix in the Hartree-Fock theory, yeah, we can manipulate equation nicely. Okay, so here I just reminded what is the density, one-body density matrix, this is the definition. Okay, so the Bra and Ket state can be any state, but in this case, we choose Hartree-Fock basis. So Bra and Ket states are Hartree-Fock states, and the definition of one-body density matrix, the KL component of density matrix is given by AL daga AK. Okay, so this is the definition. And since you can use the, fermionic anti-commutation relation, and you can show that this is only possible, it becomes finite, provides 1, when K and L are occupied states or whole states, and any other components of the one-body density matrix is 0. This is a special property of one-body density matrix in the Hartree-Fock theory. And this is just a whole component, or both indexes are occupied indexes, and any components with particle states must be 0. So this is a property of one-body density matrix. And then you can show that, easily, really, it is apparent that this is idempotent. So rho square is rho, because this is just a unit matrix in the whole component. So this is idempotent. So when matrix is idempotent, it can be used as a projection operator. So what does it mean? So if you operate rho 0, this one-body density matrix, to any arbitrary matrix A, since it has this particular form, it cut, the bottom part, particle hole and particle components becomes 0. And if you operate this density matrix from the right-hand side of A, then you can get 0 in the right-hand column here. So if you put density matrices in both sides, you can get whole component. And also, you can define the 1 minus rho 0. So this is a projection operator to the subspace of rho, let's say. And then it will provide actors in the opposite way. So you will get, by acting rho, sigma 0 from the left, you can get these bottom components. And acting from the right, you can get the right components. And then you can get, by acting rho 0 and sigma 0 in this way, you can pick up the whole component, whole particle component, particle whole component, and particle components in this way. So yeah, actually those properties are useful to manipulate the equations in the matrix form, and we will just use these relations. And this sigma 0 also satisfies these idempotent properties. And also, if you operate sigma 0 and rho 0, it becomes 0. Since this is a, you can consider that this is a projection operator. So if you operate after rho 0, the sigma 0 after rho 0, then it is 0 because it is already after the projection. So we will use just those equations. So let us derive RPA from TDHF. So here I just introduce some preparation. Okay, so now we will introduce some time-dependent perturbation to the system. Okay, so this is a time-dependent Hartree-Fock equation in the matrix form. Yeah. Okay, I just remind you, from the variation, you can get the particle whole particle component of the H is 0. And from this relation, you can operate the density matrix from the left and right. And using the property, that properties. So 1 minus rho is a sigma. So sigma h rho and rho h sigma must be 0 because this operation pick up the particle whole and whole particle components. So this is just this variational condition. And from this, you can easily obtain this commutation relation. So this is a so-called Hartree-Fock condition. So to get this, you can just see this equation. So there are H rho coming from this I, H rho and rho H, and the rest is rho H rho and rho H rho. So you can eliminate rho H rho, and the remaining terms is rho H minus H rho. So you can write down this Hartree-Fock condition using these properties of projection operators. H rho is 0. So this is a Hartree-Fock condition for the static case. And if you extend it in the time-dependent regime, the equation becomes like this. So H rho, the commutation relation of H and rho, is one side, and the other side is IH bar derivative of time derivative of density matrix. So this is a matrix formulation of the TDHF equation. And now we introduce the time-dependent perturbation described by F. So this is some arbitrary time-dependent perturbation to the system. And then after this because of this perturbation, we assume that the one-body density matrix becomes fluctuate. Fluctuate around the equilibrium value, rho 0. So the time dependence of the one-body density matrix can be written as a constant, which is the equilibrium density, rho 0, plus time-dependent fluctuation, delta rho t. Okay. So this is a basic assumption to derive the RPA. So then we require that after the perturbation, this rho t also describes the Slater determinant. So it means the idempotent property rho square equal rho must be preserved after the time evolution. So you can put this assumed form of rho t, rho 0 plus delta rho, to this equation, rho square. Okay. Then by expanding these equations, you will get this. And rho square is rho 0. Rho square is rho because of the idempotent property. And we can neglect this delta rho square because this is the second order of the small perturbation. And then to satisfy this condition, this idempotent condition, so rho square is rho 0 plus delta rho equals to rho. These terms written by red line must be delta rho. Okay. So this is a requirement to be the theta determinant after the time evolution. So delta rho must be equal to rho 0 delta rho plus delta rho rho 0. Okay. And then, for instance, from this equation, by operating from both sides, the rho 0 or sigma 0, you can get this equation. So sigma 0 is simple because there is rho 0 sitting left or right hand side of delta rho. Because sigma rho or rho sigma is 0 because of the projection operator property, then so the second equation is holds. Then, to satisfy this condition, this rho delta rho rho must be 0. Because the first and second equation provide the same, but to get the equality of left and right hand side, this must be 0. Okay. It is coming from this condition. Okay. So now we will assume this condition. So we perturb the system by some FT. This is time-dependent perturbation. And we assume that the density fluctuates with the same frequency of the perturbation. So this rho 1 is, we do not give the form of rho 1 explicitly. But anyway, we assume that delta rho can be written in this way. And this I omega t is a corresponding frequency of the external perturbation. Okay, so those are just a preparation to derive the RPA equation from the TDHF. Okay. Then I just, quickly digest how to derive RPA. So the point was, we impose the perturbation to the system, and the rho t is assumed to be rho 0 plus delta rho. And we approximate this h rho 0 plus delta rho. We expand this up to the first order in delta rho. So it can be written as h plus this term. So by putting this expanded form into the TDHF equation, and you can open up this commutation relation term by term, and you can get this equation. So this is just a substitution of these equations. Okay. And here, from the Hartree-Fock condition, the H and rho commute each other. So this vanishes from the Hartree-Fock condition. And F delta rho, this term vanish, we can neglect because F and delta rho are assumed to be the small perturbation. So this is the second order. So we will check the remaining term. And okay, so since those are H and delta rho, all quantities are the matrix in this formulation. So in the following, I just pick up particle whole component. It means index mi, particle and whole. And then from this equation, this term, you can get this condition. And the point is, okay, so this H is a single particle Hamiltonian matrix. And this matrix is in the Hartree-Fock basis diagonal with eigenvalue of the single particle energies, epsilon k. So this H matrix is diagonal with single particle energy. So you can put this condition into the equation, and then you can get this equation. So I just put the assumed form of delta rho here. So now already you have something you observed in the RPA equation from this term. And also you can consider this term. And okay, the density matrix in the Hartree-Fock basis is only one in the whole component. You can use this condition. And also the component in the which contain any particle index is 0 from the particular form of the density matrix that I introduced today. So the second term is 0. And first term, this rho 0 becomes a Kronecker delta. And it becomes particle whole component of this. And I do not draw the, do not calculate this delta H delta rho. I just leave it as it is. So this is just a usage of this condition, the particular form of one-body density matrices. And finally, this term provides you this condition. Okay, so this index mi is just I'm considering particle whole mi component. And you will have f rho minus rho f, but again, rho mi or rho is 0 if it contains the particle index. So only f rho term remains. So you get this condition. And again, this rho 0 is a Kronecker, can be written as a Kronecker delta, and you can get this condition. Okay. So by imposing some external perturbation and expanding up to first order, or let's say linearize the TDHF equation, we could derive those terms, okay, from TDHF equations. And this is just the left-hand side. So in the left-hand side, the rho dot time-dependent part is just a fluctuating delta rho. So time derivative is operating only delta rho. And then I just take this minus I omega t term. So this is the condition. So time derivative operates only on this exponential term, and then h1 omega appears. So to summarize, from the linearized TDHF equation, we could obtain for the particle whole components this equation. And actually, we can regard or define the A and B matrices in this way. So this is just to write the equation in a compact form. But okay, and but exactly the same way, you can consider the whole particle component. Whole particle means instead of MI index, you can consider IM index. And you can derive very similar equation from whole particle components. And then, actually, by regarding H rho is V bar, and rho 1 is X and Y in the RPA equation. Actually, those equations coincide with the RPA equation. So in the definition of A matrix, in RPA, you have this energy difference plus the interaction between particle and whole states. And now it can be written in this way. So anyway, in this way, from the time-dependent Hartree-Fock, assuming the small perturbation and linearizing the equations, we can derive the RPA equation in this way. So the TDHF contains actually the RPA in the small amplitude limit, but we can go further. So we can release this linear response condition, and we can describe any non-perturbative large amplitude or violent dynamics using a TDHF equation. Okay. So now, from now on, in the rest of, let's say, 30-something minutes, I will show some applications of TDHF or TDDFT for low energy heavy ion reactions. Okay, so in RPA, we can just describe some collective excitations according to some, due to some perturbation to the system. But in TDDFT, we can go way beyond RPA. So first of all, I will remind you some overview of low energy heavy ion reactions. Okay, so this was already shown in the first lecture, but let me repeat once again. Okay, so we can regard the low energy heavy ion reactions as a non-equilibrium quantum many-body dynamics. Okay, so the initial conditions are very simple. So we have two colliding nuclei, let's say the projectile and target, okay, with the proton number Z and neutron number M, okay, with certain energy, certain center mass energy, and the impact parameter. And the impact parameter is a distance from the central collision, okay, at the infinity. So for in the case impact parameter 0, it is a head-on collision. And when we have finite impact parameter, the projectile and target nuclei has certain displacement from the beginning. Okay. Okay, and what we are interested in is what happens during the collision or reactions. Okay. So when energy is smaller than the Coulomb barrier, or let's say energy is not enough to make a collision of two nuclei, we have the so-called direct reactions, which is just a simple reaction. For instance, transfer of a few nucleons through the quantum tunneling, and excitation is very low, negligibly small. So which is the so-called quasi-elastic scattering. But when incident energy is higher and higher than the Coulomb barrier, then two nuclei collide and they form a dinuclear system. So some composite system of two colliding nuclei. So this is the stage of capture. So we have dinuclear system formation, and because of this collision, we have energy dissipation, and many nucleons are transferred between two nuclei. And after certain time evolution, the dinuclear system can reseparate. Okay. So forming a different outgoing nuclei. So this is a so-called deep inelastic collision because of the large energy dissipation into the internal excitations. Or since we have many nucleon transfer, it is called multinucleon transfer reaction or quasi-fission. So this is like a fission after the certain formation of a composite system. So this is a multinucleon transfer and quasi-fission process. Okay. And then, yeah, in some certain probability, the system can overcome an inner barrier. So there is a kind of inner barrier that need to overcome to make a fusion reaction. Then a composite system, the so-called compound nucleus, is formed. So this is a so-called fusion reaction. So in this case, after this compound nucleus formation, the information of entrance channel almost vanishes. Only the excitation energy and parity and angular momentum, such kind of basic quantity remains, but the information about the entrance project and target nuclei is gone. So this is a summarized excited nucleus, and this is a fusion reaction. And after the fusion reaction, since this system is highly excited, this nucleus can undergo fission, which is called fusion-fission reaction. So since the entrance channel information is gone, this final product is much different from the entrance channel. And also we have the particle evaporation instead of fission. So the particle evaporation is just an emission of some neutrons or light particles. And those emitted particles carry kinetic energy. So the remaining system becomes cooler and cooler. So this is a process to have some evaporation residue or some heavy product after the fusion reaction. So in this way, the low energy heavy ion reactions at around the Coulomb barrier are quite complicated. And depending on the energy and impact parameter, and also the providing projectile target combinations, we have a lot of nuclear dynamics, in this way. And it is an important task to understand and describe those complicated reaction dynamics from the microscopic many-body approach. Okay, so from now on, I will show the application of the TDHF or TDDFT for the heavy ion reactions. So how can we describe such kind of complicated reaction dynamics within the time-dependent mean field approach? But it is actually quite simple. Okay, so assume that we have some kind of energy density functional. Okay, so EDF is given. So actually we have many studies of the energy density functional, and we have some quite good energy density functions that can describe nuclear properties and also nuclear matter properties. So assume that we have energy density function. Then that's it. So we do not have any empirical adjustable parameters to describe the nuclear reactions. We just use energy density function and solve constant equation and TD, time-dependent constant equation. So for the static case, we assign neutron and proton numbers for the project and target nuclei. And separately, we can solve the Kohn-Sham equation self-consistently, having the ground state of new project and target nuclei. And after getting the convergent solution of Kohn-Sham equation, we can put those wave functions into a larger computational box, okay, to describe the nuclear reactions. And by adding some relative momentum, which can be done by Galilean boost to each of the wave functions. And then by solving the time-dependent Kohn-Sham equations, we can describe complex nuclear dynamics in real space and real time without any empirical parameters. We just use one energy density function, which is the same as static case. And by solving the TDKS equation, you can get any complex reaction dynamics in this way. So this is a way how we describe the heavy ion reactions within TDDFT. Okay. So often I use this to explain what can be nicely described by TDHF. So this shows, some probabilistic process showing formation of the Gaussian distribution. Okay, so assume that we are trying to describe the complex heavy ion reactions. Okay, so after the reaction, many complicated reaction processes take place. So here something complicated happens. And after the reaction, you will observe. In the experiment, we will observe some kind of distribution of observable. So not only certain most probable process, but also in experiment, we have a bunch of distributions of outcomes with certain probabilities. So what TDHF or TDDFT can nicely describe is a most probable reaction outcome, actually. And it is known that it fails to describe the distribution or underestimates the width of the distribution of reaction outcomes. Okay. Actually, so there is a method, recently developed method to cure the drawback of TDHF, which is known as time-dependent RPA, TDRPA. By adding some fluctuations in time evolution, we can reproduce the distribution of the observable. But okay, I will skip, not going to the detail of such kind of extensions. So now I will show how TDHF works in practice in describing the most probable reaction outcome. Okay, so first example is a multinucleon transfer reactions. So here I show some typical example of reaction dynamics. So this is a collision of nickel 58 and lead 208. So the heavier nucleus is a lead 208. Okay, so with different impact parameter. So let's see. So first I show reaction dynamics for larger impact parameter from femtometer. So let me repeat. So in this case here, two nuclei approach but do not collide deeply. So only some fraction of single particle wave functions are transferred through the tunneling process. Okay, but I can show that later that even for this reaction, we have certain probability of nucleon transfer. And okay, so this is the case with smaller impact parameter, so closer to the head-on collision. So in this case, two nuclei collide more deeply, forming a dinuclear system. And during this stage, many nucleons are transferred actively between two colliding nuclei. And because of the Coulomb repulsion, eventually the system splits into two. And some reaction products are produced. So this kind of complex reaction dynamics can be described without any adjustable parameters within TDHF or TDFT.
Okay, so after the reaction, we have some, many body wave function or density distributions. So we can integrate the density in each of the fragments to evaluate what is the number of nucleons transferred between two colliding nuclei. So here I show the delta n, it is a number of transferred nucleons as a function of impact parameter. So when impact parameter is large, two nuclei do not collide. So number of transferred nucleon is almost zero. But when as an impact parameter decreases, two nuclei start colliding deeply. So here we have some transfer of neutrons from lead to nickel, and here we have transfer of few protons from nickel to lead. So the direction is different here and here. Yeah, okay, actually here. So in this region, the neutron and protons are transferred in the opposite way. And this can be understood as a charge equilibration process where we have some different Fermi energies in each nucleus, and then neutrons and protons transfer to gain energy during the collision. And from this kind of consideration, we can explain this trend of nucleon transfer at the initial stage. But if you look at this small impact parameter region, something different is going on. What is this? So actually, from the time evolution, we can see what is happening here. So in this small impact parameter region, we have a thick neck formation. And since the neck region is composed of both neutrons and protons, by the scission point, I mean, when two nuclei dissociate to two individual nuclei, the nucleons in the neck regions are absorbed by this smaller fragment. And this explains why neutrons and protons transfer in the same direction in this small impact parameter region. Okay, anyway, in this way, by just solving the TDHF equations, we can get this kind of distinct mechanism of nucleon transfer depending on the impact parameter. The first charge equilibration process and neck formation breaking. Okay, so this is the result of TDHF calculations. And yeah, maybe I can skip, but okay, so I just mentioned here that, so to compare with experimental data, we can use TDHF to describe the reaction dynamics which occurs in the zeptosecond timescale. Zeptosecond is a 10 to minus 21 second. But in reality, the excited fragment can decay through fission or particle evaporations. So to describe this kind of process, one can use a different theory, because this is the distinct processes which can be nicely explained by some statistical model. So, and time scale is quite different. So it occurs 10 to minus 18 or 10 to minus 16 seconds. So the time scale is quite different. So we can use different model of particle decay with statistical model. So we can combine those two and compare with experimental data. So maybe I can skip this. So this is just a detail, but we can actually extract the transfer probabilities from the wave function after reaction. So here, I just use this kind of projection operator. And yeah, if you look at here, so n hat v is a number operator for the fragment inside this region B. And this is kind of Kronecker delta, integral representation of the Kronecker delta. So the expectation value of n hat is equals to small n, then this operator becomes unity. So in such a way, by operating this kind of operator to the wave function, we can calculate the probability for the nucleon transfer. So I showed some density distribution, time evolution of the density, but actually wave functions are exchanged in a complicated way. And by using the particle number projection method, we can extract this kind of transfer probabilities. Okay. So actually we have transfer of many nucleons as a function of input parameter, and the probability distribute in this kind of way, in a complicated way. But anyway, again, this can be obtained from the result of TDHF calculation. And since we have transfer probabilities, we can calculate the cross-section and compare with experimental data. So here I just show some, I'm not going to the detail, but so this is a production cross-section after the collision of nickel and red points are experimental data. So they perform using the accelerator, the collision of nickel and lead, and identified what kind of nuclei are produced, and obtained those cross-sections. And then the red line and blue lines are result of TDHF calculations. And again, without any empirical adjustable parameters. We just take a energy density function where known EDF, then calculate the collision and extract the transfer probabilities, and then evaluate the cross-section. And then, we can get the certain qualitative or quantitative agreement with experimental data. But there are some deviation with experiment, and it can be actually improved by using the time-dependent RPA. But I'm not discuss this kind of extension here. So anyway, TDHF can provide some quantitative reproduction of the very complex reaction dynamics and experimental data. Okay, so now I will show another example, the Quasifission process. So this is related to the synthesis of superheavy element. So Quasifission, what was the Quasifission? So Quasifission process occurs after the capture, and for certain probability, the system gets fused, forming the compound nucleus. But the Quasifission is actually the process that hinders the formation of the compound nucleus. And the evaporation residue cross-section, the formation of the final fusion product, can be given with this kind of simple formula. The PCN is a compound nucleus formation probability, and sigma is a capture cross-section, and WSURB, this is a survival probability. Okay, and this PCN is close to 1 in case of heavy system forming the super heavy elements. So the Quasifission process is a dominant process that prevents the super heavy element synthesis. And this kind of main reaction dynamics can be well described by TDHF. And I just show, okay, so here I just show this animation. So this is a case for uranium and nickel. And if they merge, they form the element 120. So this is a very heavy system. And since the uranium-238 is well deformed, we should consider the orientation dependence of reaction dynamics. And in case of tip collision, we have shorter contact time and For side collision, we have longer contact time with compact dinuclear system and many nucleon transfer. And in this case, about 36 nucleons and 50 nucleons are transferred on average. And this kind of quasi-fission dynamics can be well described by TDHF in this way. And this is just a comparison with experimental data. So left figure shows the result of TDHF calculation, and the right figure shows the experimental data. And the experimental data shows some distributions. But in TDHF, here I just show the average number of reaction outcomes. And TKE is the total kinetic energy of the outgoing fragment. So kinetic energy. So it means those two peaks around 64 and 238 corresponds to the quasi-elastic scattering. It means with larger impact parameter, they do not collide. So we do not have energy dissipation. So TKE, total kinetic energy of the outgoing fragment, is equal to the initial value. So without energy dissipation. And when they two nuclei collide, energy dissipates into the internal excitation. So TKE drops in this way. And after energy dissipation, the nucleons start transferred towards from heavy nucleus to the light nucleus. So the horizontal axis is the mass number. So the mass number changes from the initial value to this kind of values towards the mass symmetry. And those amount of energy dissipation and amount of nucleon transfers on average nicely agrees with experimental data. So again, without any adjustable parameter based on microscopic approach, the TDHF can describe the quasi-fission dynamics quantitatively in this quality. Okay, so and this is probably the last topic. So synthesis of super heavy element. Okay. So this is a hot topic of hot and challenging topic in the nuclear physics community. So in the accelerator facilities like RIKEN, they collide nuclei and try to produce new unknown unstable nuclei. And one example is a fusion reaction. So they collide two nuclei and merge and then form some heavy elements, like super heavy elements. So actually this RIBF, radioactive ion beam factory, RIBF is a world-leading factory of unstable nuclei. So the point is, maybe you know that the periodic table, is growing. I mean, putting some new elements, and it is already, about 9 years ago. So 4 elements have been added to the periodic table: nihonium, moscovium, tennessine organeson, and nihonium element 113 is discovered by the scientists in RIKEN. And we got some naming license, and we put the Japan in Japanese Nihon and put the nihonium, name nihonium. Okay, so this is a very important subject, and actually that was the first Asian country that discovered the new elements. So this was very important meaning in scientific history. And so this I just showed this. We had some ceremony of 150th anniversary of the periodic table in 2019 in Tokyo. This is Tokyo Prince Hotel, and we nuclear physicists gathered to celebrate this anniversary. And he is Morita-san. And I bought, this is just an advertisement, but I just bought the necktie at this symposium, and then you can see this is a Mendelevium 150th anniversary International Year of Periodic Table 2019, yes, and 4 new elements. Yeah, and it can be found in this front side of the necktie. So I recently used this necktie actually for some retirement of my supervisor. Anyway, so since the time is limited, so I just briefly mentioned that the synthesis of nihonium was very tough. I mean, it was very difficult. So in accelerator experiment, about 10 to 12 nuclei are irradiated as a beam to the target. So it is enormous amount of nuclei. But so they started experiment from 2003. Then after 100 days of irradiation, they got first event. But okay, and then after again 100 days irradiation, they could produce second event. But those two events are not enough to show the successful production of element 113 because the final product decays through fission, and that was a minor decay process, and that was not enough to show the evidence. So they continue the experiment, but it takes about 7 years. Then after that, finally they obtained the third event, and it decays through the alpha decay, and it becomes a it agrees with the non-alpha emission data. So then with those 3 events, they could get finally the naming license. Okay, so this is just the final topic. So yeah, so as I mentioned in some of the previous lecture, so the next shell closure is expected in the super heavy region around proton number 114 or neutron number 184, somewhere here. And this shows the northeast part of the nuclear map. And this color map shows the lifetime, expected lifetime. So because of this shell closure, it is expected that the super heavy nuclei in this region may have the half-life, quite long half-life. Okay, so this is the so-called island of stability. And people are trying to reach this island of stability, but this is really difficult. Okay, so this is just a cartoon showing the situation towards the island of stability. And yeah, cold fusion is a reaction like what nihonium was produced. But now the hot fusion reactions is the only way to produce the element up to 118 organeson. So now using TDHF or TDDFT, we like to predict what is the best way to produce super heavy nuclei. So since the TDDFT is microscopic framework without empirical parameters, so it has some certain predictive power. So we are now trying to do such kind of predictions, and this is just one example showing the fusing nuclei in case of vanadium curium. If they fuse, they form the unknown element 119. And yeah, this kind of TDDFT simulation can be performed on a supercomputer. And yeah, we are trying to produce such kind of predictions. So now, since time is up, I will just skip. So I just skip here. So this is just an extension to combine TDHF and Runge-Gross type approach to connect the result of TDHF calculation to the super heavy element synthesis. Yeah, I will just. I just say, yeah, in TDDFT or TDHF, only input is the energy density functional, And based on the variation principle, we can get TDKS or TDHF equations. And we can describe not only the nuclear dynamics in the finite nuclei, and also the dynamics of the neutron star, inside the neutron star, which we will discuss in the next lectures. But it is very powerful framework. And this is a summary message. So as I mentioned, the TDHF can describe nicely the main reaction outcomes, multinucleon transfer, energy dissipation, quasifission process. But there are some limitations. But nowadays, I didn't explain, but we can apply some kind of extended approach like stochastic extension or time-dependent RPA to include the fluctuations and correlations, or combination with Runge-Gross approach, we can also apply to the superheavy element synthesis. So the time-dependent mean-field approach is a very powerful, useful framework to describe nuclear reaction dynamics and many other phenomena in a time-dependent and microscopic way. Okay, so this is a summary. So thank you. So this is the end of this lecture.